Yeah, very good evening, one and all. I hope I'm clearly audible and my screen is visible in the full screen mode.
Yes, sir.
Yes, sir.
Yeah,
Yes, sir.
all right. Yeah, sorry that I have informed you late because till 7 o'clock till 6:55 I had some meeting. So that's why I informed. I have seen the voting that time. Fine. So in this session, we'll be discussing about the decision trees, which is also one of the classifier. Decision tree classifier is there, regression is also there. We'll be discussing it in the context of the classification. So what is the decision tree and how to build a decision tree with an example we'll see in this session. All right. So we'll start with a simple example that whatever that we have seen, right? Classification of the insect type. And let's say that this is the distribution of the insects, katydids as well as the grasshoppers. Katydid is indicated with the red color, grasshopper is indicated with the blue color circles, as you see in the figure, right? So if you take this decision tree, what decision tree does is that it takes a sequence of decisions on the attribute values. Takes a sequence of decisions on the attribute values to classify the instances. So like for example, here you see that at the root node, it is taking a decision on the abdomen length. If the abdomen length is greater than 7.1, which is corresponding to this decision, right? So if the abdomen length greater than 7.1, it is directly assigning the label as a katydid, as all the instances with greater than 7.1 abdomen length are here katydids only. So that is why it is directly assigning a label called katydid. If it is less than 7.1, there is still some confusion. You cannot say it is directly grasshopper because there are few instances that belong to belong to katydid as well, right? So it means you need to take another decision to decide whether it is a grasshopper or not. The decision that you are taking here is on the another attribute value, which is the antenna length. So if the antenna length is greater than 6.0, then again you are classifying it as a katydid. Otherwise, you are classifying it as a grasshopper, right? Classifying it as a grasshopper. So it is taking a sequence of decisions on the attribute values to make a classification, right? So these decisions are organized in a tree-like fashion. We call that as a decision tree. So at each internal node, we are taking a decision or we are checking a condition on the attribute values. According to the attribute value, we'll be taking one of the path, right? And then checking another attribute value at the next internal node, and this will be continued till you reach to the leaf level. So leaf node, you will have the attribute value, right? Class label. At the leaf node, you have the class label. So understood, right? What is the decision tree? How to construct, we'll see. Don't worry about it. Understood, right? What is the decision tree? Everybody,
Sir.
you following?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Fine. So we'll see one more example so that it will be more clear to you. So here is the decision tree example. At the root node, we are checking a age attribute, and age takes three values, either youth, middle-aged, or senior. So for each of the possible value, we have one path. And at the next internal node, we'll be checking another attribute values, and based on them, we will be proceeding further. At the leaf node, you will be assigning yes or no label to it. Here, the internal nodes or leaf nodes are the class predictions, internal nodes are the attribute value test, and edges are the attribute values, right? Edges are the attribute values. So the leaf nodes are the class predictions, intermediate nodes are the attribute value test, and edges are the attribute values. These are the various example algorithms for the decision tree, right? So decision tree, what it is doing is that it is taking the training data set and it is checking the various attributes. Let's say these are the attributes. So based on one of the attribute, it is applying some condition on one of the attribute. Let's say A4 is the attribute. We'll see how to choose the attribute at the root node and so on. We'll be seeing later. But let's say A4 is the attribute. And let's say A4 is taking three values X, Y, Z. X, Y, Z. So these are all the instances that takes A4 as a, attribute 4 as a X. All these are the instances with a value X on attribute 4. And all these are the instances with the value as Y at attribute 4. And all these are the instances with A4 equal to Z, right? So if you see this node is a pure node. All the instances belong to a single class. That is why indicated with a plain color red. So all the instances belong to a single class. It is a pure node. So therefore, you can assign a label red to this, all the instances, right? You can make it as a leaf node. But here, you still see that there is a mix of classes. Instances belong to the different classes, not just a single color, right? So therefore, you need to apply further test on these nodes, right? So this is a pure node. You can make it as a leaf node with a class label red. But these are impure nodes. It means you have to proceed further to select the best attribute and continue it, right? So depending on whether the node is pure or not, will be deciding whether to proceed further or not. If the node is pure, then we'll not be proceeding, declaring that as a leaf node. If the node is impure, we'll be continuing further by selecting another attribute at that node, right? How do we decide whether it is a pure node or not? If all the instances belong to the same class, we say that it is a pure node. If the instances belong to the more than two classes, we more than or equal to the two classes, we call that as a impure node. Okay. So let me give you an example for this. Let's say that I have given you two bowls, two bowls. So let's say in one bowl we have 100% milk. In the second bowl, I've got 50% milk and 50% water. Which one of this bowl is pure? Which one of this bowl is impure?
First one is pure.
First one is pure and the second one is impure, right? So let's say that I've given you two drawers. In the first drawer, I've got 5 red color balls. In the second drawer, I've got 3 blue balls and 2 red balls. Which one is pure? Which one is impure? First one is pure, the second one is impure. So how did we say that? If all the instances belong to the same class, then we call that as a pure. If the instances belong to the multiple classes, then we call that as a impure. It means there is a further distinction required to distinguish between the instances from the two different classes or more than two different classes, right? So we call them as the impure nodes. So attribute value tests are required for those nodes. Means we have to continue further by selecting the best attribute at that node. Okay. So, all right. So let us say that somehow you have constructed this decision tree. How to classify a new instance is the question. We'll see how to construct a decision tree later, but let's assume that you have already constructed the decision tree and now you want to classify a new instance. Let the decision tree is this and the new test instance is this, right? So at root node, what is the attribute that it is taking? Refund attribute. So what is the value that the test instance is taking on the refund attribute? Value no. So should I take the right path or left path in the decision tree?
Right path.
Right path we have to take, right? So we proceed to the right path. At the next internal node, what is that it is checking? Marital status. What is the value that this new instance is taking on this marital status? Married. Should
Married.
I take the left path or right path?
The
Again
right
right path. So, and then this is going to the leaf node and classifying it as a no, right? So check the refund attribute, which is taking a value no. So therefore proceed to the corresponding edge, which is the right edge. Then check the next attribute, which is checking the marital status. And this is also taking the right path. And finally you reach it to the leaf node and assign a cheat to the no, right? Whether the person will cheat or not. That's what the question is, right? Based on the some characteristics. preferred marital status, taxable income, and so forth. Fine. So this is how we can test a new instance or predict for the new instance. Now the question is that how to build this decision tree, right? How do we decide which attribute to be selected at the root node, which attribute to be selected at the next internal node, and so forth? How do we decide that? We decide it based on the greedy strategy. Are you with me so far? Following, right? Am I going too fast?
No, sir.
It's fine, right? Following, right?
Yes,
Yes,
sir.
sir. Yes, sir.
Yeah, yeah. So how to build a decision tree? So we follow a greedy strategy in a sense that we split the records based on the attribute test that optimizes certain criteria. We split the records based on an attribute test that optimizes certain criteria. So it means whichever attribute is optimizing certain criterion, we select that attribute in the root node, right? Or at that particular node, right? So now few initial questions that immediately comes to us is that how to split the records, right? How do we determine how to split the records, or how to specify the attribute test condition, or how to determine the best split, or how to determine when to stop splitting? So these are the some of the initial questions that comes to our mind. So let us try to answer each one of these questions one by one. Okay. How to specify the attribute test condition? We choose the attribute that leads to the greatest increase in the purity. Okay, we choose the attribute that leads to greatest increase in the purity. Let me demonstrate this with the help of an example. So let's say that there is a set of instances, 100 instances. Okay, 100 instances, and let's say that 50 of them are class 1 and 50 of them are class 2, right? And let us say each one of these 100 instances are described with two attributes, A1 and E2. Suppose if I split the data based on the attribute A1 value, and let's say that A1 is taking two values, X and Y, and A2 is taking two values, A and B. Oh, A and B, 9, something will take, what is that, L and M. Okay, so if you split the data based on A1, so the data is splitted like this. All there were two values I said, right? X and Y. So here, all the instances that take value X on attribute 1, if I take this, there are 25 instances that belong to class 1, 25 instances that belong to class 2 here. And similarly here also 25 instances that belong to class 1, 25 instances that belong to class 2. It means 50 instances are coming here, 50 instances are coming here that takes attribute value Y, attribute 1 equal to Y, and out of them 25 belongs to class 1, 25 belongs to class 2. If I split it based on attribute 2, it is taking two values L and M. Okay, so 50 instances coming here, all of them are class 1. 50 instances coming here, all of them are class 2. So now tell me which one of this attribute is leading to the greatest increase in the purity? A1 or A2?
A2.
A2 is leading to the greatest increase in the purity, right? It
Yes,
means
sir.
based on which attribute if you split, it is leading to the greatest increase in the purity. You choose that attribute. Choose the attribute that leads to the greatest increase in the purity, right? So there are some measures to do that, to compute what is the greatest, increase in the purity, right? So that using those methods, we will be selecting the attribute. That we will see later. But have you understood what do we mean by greatest increase in the purity with this
Yes, sir.
example? Yes. And this depends on different things. It depends on the attribute types, depends on the number of ways to split. Okay, so the attribute type can be either nominal Ordinal or continuous? Continuous, we know it can take any value. Ordinal means what? This is discrete type only, but there is some order present in the values. Like for example, if you take small size as the attribute, and let's say that it is taking three values, small, medium and large. There is some internal order present in this, right? Small is less than medium, medium is less than large. Am I right? So this type of attribute, we call it as the ordinal attribute. It is a discrete type, but there is some order present in the attribute values. Nominal is that this is also discrete, but there is no specific order. Let's take an attribute color, and let's say that there is taking three values, red, green, blue. Right? Can you define any order that red is less than Z is less than B, something like this? Not possible, right? Everything is equal. I mean, you can't define the order among them, right? So this kind of attribute, we can call them as a nominal attribute. So ordinal and nominal, both of them are discrete, but the difference is that in the ordinal data, we have some meaningful order present among the attribute values. Whereas in nominal attributes, there is no specific order. Understood the difference, right? Nominal, ordinal, and continuous.
Yes, sir.
Yes. And this is also depending on number of ways to split. The possibilities are two-way split and multi-way split. We'll see with example, you will understand it. So this is a multi-way split. Let's the attribute is car type and it is taking three values. Family car, sports car or luxury car. Three values are possible. So if you are defining one edge each for each possible value, we call it as a multi-way split. There are three values. For each one of the value, we have one edge defined here. This is a multi-way split. If it is a binary split, we will be dividing these possible values into two disjoint groups. Like you can either group sports and luxury one, family another. You can either group family, luxury one, sports another. Or what is the other possibility? Sports and luxury one, sports and family one, and luxury another. Okay, so these are the possible groups, right? So divide the values into two subsets, and you need to find the optimal partitioning. Which one of this subset is the optimal partitioning that we need to determine if you are going with the binary split. This is with the nominal attributes. If it is the ordinal attribute, multi-way split is same as in case of nominal attributes. Let's say the size, small, medium, large. So the multi-way split, each one edge for each one possible value. What if the binary split, right? What are the possibilities? Small, medium versus large, a small versus medium, large. But does it make any sense to make this grouping, small, large versus medium? If there is some ordinal information is there, doesn't make any sense, right? So we'll
Yes,
not
sir.
check for these kind of splits in case of ordinal attributes. Okay, so it depends on either it is a binary split or multi-way split, and what is the type of the attribute also. Okay, and how to split based on the continuous attributes. Continuous attribute means there are not fixed number of values, right? It can take any value, and there are a lot of possible values, right? So we can't take each one edge for each one of the possible value because this is infinite number of possibilities, right? So how to handle the continuous attributes is the question. How to handle continuous attributes? I hope everybody is following so far. Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, following, right? So because I felt like I'm continuously speaking, so I am not sure whether you're following or not. Is it okay? Are you with me?
Yes, sir.
Yes.
Yes, sir.
Yes.
Yes, sir.
Yeah. Fine. Splitting based on the continuous attributes. So if it is a continuous attributes, there are many values possible, right? How to handle the continuous attributes? There are different ways of handling continuous attributes. One is discretization. It means convert these continuous values to the discrete values. Like for example, you take age attribute. Age can be any value, right? It can be 0 to 100, any value, right? So now, suppose if I discretize it, I can say that anything less than 20 age is a teenage, anything 20 to 40 is a young age, anything 40 to 60 is a middle age, anything above 60 is a old age, right? That means I am just mapping the continuous values into 4 buckets. This is one way of discretization. We call it as the static discretization, right? The static discretization, which means discretize once at the beginning, right? So dynamic discretization is also there. Ranges can be found by some equal interval bucketing or equal frequency bucketing, and then or use clustering. There are different ways you can create these buckets and map these continuous values to the discrete values. Okay, basically you're just trying to discretize the continuous values and placing each one of the continuous value into one of the bucket, right? This is one possibility, discretization. Clear the idea of the discretization? Is that clear or should I repeat?
Sir, repeat. Can you repeat once?
Yes. So let me take age as the attribute. Age as the attribute. If I take the age as the attribute, there are many possibilities. It can be age 1, age 2, 1.5, it can be 3, it can be 10, it can be 20, it can be 50, it can be any value, right? Right. So,
Yes,
but
sir.
I can't take one edge for each one of the possibilities. There are so many edges if I do that, right? So, there should be some way to map these values to discrete values. So what we do is that we discretize the input. It means let's say that I'm creating 4 buckets. One is the teenage bucket. The other one is the youth bucket. The other one is the middle age bucket. The other one is the old age bucket. Now I define some thresholds. Like I say that anything less than or equal to 20 age, you assign a teenage. So it means instead of 1, I can assign teenage. Instead of 2, I can, if you want, you can create another bucket. Less than 10 is a child, right? So it doesn't matter. Don't say that, are you assigning teenage to, I mean, age 1 person. Okay, don't ask me that. I'm just giving some example. Okay, so teenage. This is teenage. Teenage. 50. 50 goes to which bucket? Middle age bucket. Assign middle age. Now, how many possible values for this attribute? 4 possible values, right? Isn't it a discrete value? Discrete attribute now?
Yes,
It
sir.
means you're converting the continuous attribute to the discrete attribute. That is how we are handling, that is how one possible way of handling the continuous attributes. Is it clear now?
Yes, sir.
Yes. So this discretization, you can either do it static way or the dynamic way. Static way is whatever that I have demonstrated now. Discrete ones at the beginning. Dynamic way is like there are ways that you can create dynamically, like equal interval bucketing. Like you say that you sort them according to the ages. First 20 of them will be the one bucket 1. The next 20 will be the next bucket 2, and so forth, like that. Or equal frequency bucketing, or you can make them clusters, right? So there are various ways that you can discretize them. Okay. So in the slides, although I'm not demonstrating that in detail of this, okay, I will share you the slides in which the ways of discretization is also present. Okay. Another possibility is binary decision. Binary decision, like you can say that age less than or equal to 40 is one side, age greater than or equal to 40 is another side. Like you said, no, you very beginning slide, you remember what was that? First condition, abdomen length greater than 7.1 is the question, right? If yes, go right side. If no, go left side. Here again you're asking, antenna length greater than or equal to 6.2. If yes, go left, right. If no, go left, right. So this is, we call it as a binary decision. So the continuous value, you are applying a binary decision by setting some value, threshold here. So for this, you have to consider all the possible split and find out the best cut. Okay, that is computationally more intensive. So understood, right? How to handle the continuous attribute, both the types, discretization as well as the binary decision. Two things are clear?
Yes, sir.
Yes, sir.
Everybody, no, madams, you guys are not responding today.
Yes,
What happened?
sir.
Yeah, thank
Yes,
you,
sir. Value, we are shifting them to the
Yeah.
mind. Yes, sir, we are clear.
Okay, fine. Thank you. So how to determine the best split? How to determine the best split? Okay, so let us take an example. So before splitting, let's say that there are 20 records of class 0 and 20 records of class 1. And let's say that there are 3 attributes: own car or not, car type, student ID, right? So if you split these records based on the own car type, own car takes 2 values, S and no, right? So if you split them based on own car, here 10 instances are coming, here 10 instances are coming. In these 10 instances, 6 of them are class 0, 4 of them are class 1. Similarly here, 4 of them are class 0, 6 of them are class 1. If you split it based on the car type, this is how it is splitting. It takes 3 values. Here 4 instances are coming, out of them 3 are class 1. Here 8 instances are coming, all of them are class 0. Here 8 instances are coming, 7 of them are class 1. If you split them based on student ID, only one instance is coming at every node because the student ID is unique, right? And everywhere it either belong to class 0 or class 1, right? So now tell me which test condition is best according to you out of all these 3. I mean to ask you that which one of these test condition making the data more pure?
Sir, student ID.
Student ID making it more pure, but what is the problem with this?
Card type.
Problem is it is unique, right? It means if you want to classify a new instance, that new instance also will be having a different ID. How do you classify it? So this is not a best test condition, right? So among these two, which is best?
Card type.
Card type. This is making the data more pure, right? As compared to this, right? If you see this, 60% class 0, 40% class 1. Similarly here, 40% class 0 and 60% class 1. It's almost like very impure, right? Highest form of, close to the highest form of impurity. See here 100% class 0, right? Here around 87% class 0, here around 75% class 1. Okay, so which one of these two attributes making the data more pure? Card type or own card?
Card type.
Card type, right? So the card type is more making the data more pure, right? So how to determine the best split? We use the greedy approach. It means nodes with the homogeneous class distribution are preferred, right? So you look at these two examples. Which one of these is a more pure or more homogeneous? This one or this one? Second one, right? You see that the first one, equal number of class 0 and class 1 instances. So this is the highest degree of the impurity. Whereas if you see that 90% class 0, only 10% class 1. This is the low degree of impurity, right? So this is of homogeneous. This means most of the instances belong to one type only. Whereas it is non-homogeneous because there is a mix of instances from the two different classes. Okay, so the nodes with homogeneous class distribution are preferred. It means we need some measure of node impurity, right? We need some measure of node impurity. There are different measures of node impurity. Popular ones are entropy, Gini index, and misclassification error. So in this class, I'll be discussing about entropy only. In the slides, I will give you the Gini index also. Okay. So entropy is, we can say, is that degree of the impurity, right? It's a some kind of measure that indicating the degree of the impurity. So I'll tell you how to compute this entropy. Okay, how to compute this entropy. Fine. I hope you're following the session. Clear, right? So far, are you with me?
Yes.
Yes, sir. Yes, sir.
Okay, thank you. Thank you. So we'll define entropy. Entropy is some kind of impurity, right? So entropy is defined this way. Entropy of the set of examples is relative to the binary classification. We'll see with respect to the binary classification first, then we will extend it to the multi-class classification. So the entropy of S with respect to the binary classification is minus P1 log P1 minus P0 log P0, where P0 is the fraction of negative examples and P1 is the fraction of positive examples. P0 is the fraction of negative examples and P1 is the fraction of positive examples. Okay, so let me take an example. Let's say that there are 10 instances and all of them belong to class 1. All of them belong to class 1. Isn't it the highest degree of the impurity? Sorry, purity? Lowest degree of impurity, isn't it?
Yes. Yes, sir.
If there are 10 instances, all of them belong to class 1. It means class 1 we have 10 instances, class 0 we have 0 instances. So what is the fraction of positive examples? P1, 10 by 10, 1. What is the fraction of negative examples? P0, 0 by 10,
0
which
by
is
10.
0, right? So compute this. Minus P1, it means minus 1 log 1 and minus 0 log 0. This is anyhow 0 and log 1 is also 0. So this is 0. It means what? Impurity is 0. It means purity is 100%. Am I right? Hello? Isn't it?
Yes, sir.
Yes, sir.
Right. So that's what this means. Similarly, if you take, let's say that there are 10 instances, 5 of them are belong to class 1 and 5 of them will belong to class 0. This is the highest degree of the impurity, isn't it? Equal mix of class 1 and class 0 instances. So what is P1 here? 5 by 10, which is 0.5. What is P0 here? This is also 5 by 10. This is also 0.5. Substitute here 0.5 log to 0.5 and 0.5 log to 0.5. This will be equivalent to 1. Okay. So the entropy is a maximum of 1 if the examples are equally mixed. You can compute that and see in the calculator, in the calc, right? So this will be 1. So depending on the purity levels in the example, this entropy value will vary in between 0 to 1. 0 means the lowest degree of the impurity, 1 means highest degree of the impurity. Fine. So this is how we compute the entropy or impurity for the binary classification. What if it is a multi-class classification problem? Multi-class means there are k classes, right? K is greater than 2. And P1 is the fraction of class 1 instances, P2 is the fraction of class 2 instances, and so on. Pk is the fraction of class k instances. So we compute this using sum over minus pi log pi. Okay, this is how we compute the entropy for the multi-class problems. Is it clear? Entropy?
Sir, one question, sir.
Please.
Sir, this entropy is in decision tree. We have to take which branch give the highest decision and ID3 algorithm, sir. Same thing. This entropy same, sir.
Same.
Yes, sir.
In the ID3 algorithm, you are computing the gain, right?
Yes, sir.
Gain.
Gain. Yes, sir.
Gain is what? The reduction in the entropy that we're gonna see. This is ID3 algorithm we're gonna discuss.
Okay. Same entropy is there, no, sir? Same
Yes,
entropy.
yes. Entropy is the same. Yes.
Okay.
Yes.
Thank you, sir.
That's the same
Thank you.
entropy. Yes.
Rocks.
Yeah, you see this. This is the entropy distribution according to the number of positive and the negative examples. Here you see that. So all there are some 10 examples. All of them are negative. So the entropy is 0 in this. All of them are belong to same class. Entropy is 0. Here also 10 examples. All of them are positive. In this case also entropy is 0. Right. So this x-axis is indicating fraction of positive. When the fraction of positive is 0, in that case also entropy is 0. When the fraction of positive is 1, in that case also entropy is 0. The fraction of positive is 0.5. It means fraction of negative and fraction of positive, both of them are same. Then highest degree of the impurity, which is 1, right? So depending on whether it is, what is the value of fraction of positive, it can be anywhere in between 0 to 1, right? Lowest is 0, highest is 1. Okay. So this is the distribution of the entropy values according to the fraction of positive. Right? Clear? Shall we move on?
So once again, this graph.
Yes, madam. Any query, madam?
Yes, sir. Can you just repeat this
Repeat. Okay.
graph?
Madam, what is the entropy giving?
Impurity.
Degree of the impurity, right? It means if all the instances belong to the same class, what is the impurity? 0?
Yes.
Right. So you see these two cases. All the instances belong to negative. It means fraction of positive is 0. So the impurity is 0. Similarly, this case. Fraction of positive equivalent to 1. It means all the instances belong to class 1. Say class positive. Class 1 or class positive class. In this case also entropy is 0. Got it, madam? These two cases?
Yes, sir. Yes. These two I got.
Suppose impurity is 1. When we say impurity is 1, when the equal mix of positive and the negative classes, it is the highest degree of the impurity, right? It means fraction of positive is 0.5. Therefore, fraction of negative is also 0.5, which is this case. 5 instances belong to positive, 5 instances belong to negative. Then you got the entropy of 1, highest.
Yes, sir. Now let's see.
Yeah, so depending on the fraction of positive, it can be anywhere in between 0 to 1. These are the different cases.
Okay.
Got it, madam? Yeah.
Yes. So preferable is the one which is having the least
Least
entropy.
entropy. Got it, madam? Yeah.
Yes, sir.
Yeah. Information gain. Actually, I said no, that we select the attribute based on some greedy criteria. Okay, you can directly say split it based on the entropy also, right? There is the information gain which we define with respect to each and every attribute, which is the expected reduction in the entropy resulting from splitting on that feature. It means whichever attribute reducing the entropy more, okay, then we select that attribute. Okay, so let's say that there is a data set. There is a data set in which we have 10 instances. Okay, 10 instances. 5 of them are positive, 5 of them are negative. Okay, so what is the impurity here? Impurity is 1, right? Impurity is 1.
Yes, sir.
Before splitting, okay, let's say that there are 2 attributes that describe each and every instance. Attribute 1. If I split it based on attribute 1, 5 instances are coming, all of them are positive. 5 instances are coming here, all of them are negative. And if I split it based on attribute 2, let's say 5 instances are coming here, 3 of them are positive, 2 of them are negative. 5 instances are coming here, 3 of them are negative, 2 of them are positive. Okay, so which attribute is reducing the impurity more?
One.
1, right? So
Yes,
this is
A1.
before splitting, this is the impurity or entropy. After splitting, if you see here, this is the 0 impurity here, 0 impurity here. So on an average, this is also 0 impurity, right? So here it's not 0, it's not 0.5 also, but it is close to 0.5, right? So some positive value, so which is greater than 0 here, greater than 0 here. If you take the average also, it is greater than 0, greater than 0. So before splitting, it is 1. After splitting also, it is greater than 0, but less than 1. Before splitting, it is 1. After splitting, it is equivalent to 0. Okay. So which one of this is reducing more? If you see attribute 1, 1 minus 0. This is the expected reduction in the impurity, that is 1. If you take this attribute 2, 1 minus some greater than 0, which is less than 1. So which one of this attribute reducing the impurity more? Attribute 1. Hello? Should I repeat? Repeat? Should I repeat?
So this last section, 1 minus 0.
Okay. You understood this, right? Before splitting, the entropy is 1.
Yes, yes,
After
that we
splitting, the
understood.
entropy is 0, 0 here. After splitting attribute 2, it is greater than 0 entropy here because it's not 0 impurity, right? Some positive impurity. So I don't know the correct value. That is why I'm just taking it as a greater than 0. So here also some positive impurity, not 0 impurity. I hope all of you agree.
Yeah.
Right? Here also greater than 0. Here also greater than 0. Right? But it is less than 1. Please see that. It is not less than, it is not 1. Right? It is less than 1, greater than 0. Okay. So let's say that some values let us take. Okay. Some value I'm taking. Some 0 0.6. 0. It's not 0.6 exactly, but just to make you convinced, I'm just taking 0.6. Okay. This is the impurity at this node. Let us say, okay, this is the impurity at this node, 0.6. This impurity is 0, this impurity is 0, right? So what is the expected reduction in the impurity if I take attribute 1? If I split based on attribute 1, that is what I am measuring. So before splitting, what is the entropy?
1.
After splitting, what is the entropy? After splitting based on attribute 1, what is the impurity? Average impurity.
0.
Right. So 1 minus 0. This is the expected reduction in the impurity. Right? Right?
Yes.
So this is attribute 2. If I split based on attribute 2, what is the entropy before splitting or impurity before splitting?
1.
1. And what is the entropy after splitting?
Some value, but less than 1.
0.6, let's say, on an average, because it is 0.6, 0.6. This is 0.4. Right? So now, splitting based on which attribute is better for us? Whichever attribute reducing the impurity more, that attribute is better. Isn't it?
Yes.
Right. And which attribute is reducing the impurity more? Attribute 1. And that we measured through the gain. So what is gain? Gain of an attribute F is the expected reduction in the entropy resulting from splitting on that feature. It
So
means
can we say like this, which attribute is leading us to get more information for
Yes,
further
yes.
classification.
Yes, yes,
Right?
yes, exactly. Yes, exactly. So this is the entropy before splitting, and this is entropy after splitting on an average. After splitting, you will get multiple entropies, right? So compute entropy at each and every node, take the weighted average of that. So subtract entropy before splitting minus entropy after splitting. This gives us the gain. So whichever is maximizing the gain, we select that attribute. Got it right? Got the idea? We'll see the example, then it will be more clear to you, but I just want you to understand the intuition behind it. Is the intuition clear? Please, if yes or no, you can say anything. I can repeat.
Sir, okay, sir, nice. You can go ahead.
Everybody, Ash, Ravi sir,
Yes, sir.
everybody. Yeah.
Sir, we are following, sir.
Yeah. Thank you. So we'll see an example that will be more clear to you. Okay, so here is an example. We want to classify whether play tennis is yes or no based on various features like outlook value, temperature value, humidity value, wind value, and so on. Okay, so this is the data set. So before splitting based on any attribute, compute the entropy. What is the entropy? Fraction of positive log positive minus fraction of negative
Log negative.
negative, fraction of negative. So look at this, there are two classes only here also. How many positive and how many negative? How many yes, how many no? What is the fraction of positive?
5 no.
5
5
no.
by 14.
Fraction of negative is 5 by 14. Fraction of positive is
9 by 14.
9 by
9 by
14.
14. So what is the entropy value? Minus 9 by 14 log 9 by 14 base 2 minus 5 by 14 log 5 by 14. Okay, so this gives the entropy before splitting or impurity in the data, right? So compute that. So this is the entropy of the data set S, so which is equivalent to 0.94. Okay, suppose if I split it based on the outlook. Okay, so what are the possible values for outlook?
Sir, 3.
Three possibilities: sunny, overcast, and rain. Three possible values. Tell me, if I split it based on the outlook. Okay, so three possible values: sunny, overcast, and rainy. How many instances will come here?
Sir, 4.
4 only. 2 here, 2 here.
Sorry,
3,
sir.
5. No?
5.
Five.
5.
How many of them are positive? How many of them are negative?
2 positive, 3. Sorry.
2 positive, 3
Negative.
negative, sir.
2 positive, 3 negative. Outlook. How many?
Overcast.
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 4. 4 of them are positive. Huh?
Yes, sir.
Okay. Here rain. 5 plus 4, 5 1. 2 negative, 3 positive. Is it? Rain. 3 positive,
Yes, you are right, sir. You are right.
2
3
negative.
positive.
Okay. So now before splitting, this is the entropy. Now measure this entropy after splitting. What is the entropy here? What is the entropy here? 2 by 5 log 2 by 5 minus 2 by 5 log 2 by 5 minus 3 by 5
3 by
log
5.
Okay. Similarly here, can you measure the entropy here? Minus 4 by 4 log 4 by 4 minus
4
0
by
by
4.
4
0 by
log 0 by 4. Similarly here, what is this?
minus 3
Minus
by
3 by
4.
5 log 3 by
5.
5 minus 2 by 5 log 2 by 5. Okay, so this is anyhow 0. 0. Okay, so let us take this is some x value. We don't know what it is, x. Let us say this is a y. Okay, and this is 0 anyhow. Leave it. Okay, so now before splitting it is 0.94. What it is after splitting? After splitting x and y, right? You have to take the weighted average, right? What is the weighted average? How many instances are here? 5 instances. 5 out of 14, right? So 5 by 14 times x plus 0, because 0 here and 4 instances are here, 4 by 14 plus how many instances are here? 5 out of 14. 5 by 14 times
Y.
right? You take that, whatever x value that you get here, whatever y value that you get here, you take this, subtract, you will get the gain of this outlook. Similarly, compute the gain for the temperature, humidity, wind, select the attribute that maximizes the gain. Okay.
Sir, why we subtract?
To subtract basically to understand how much impurity it is reducing. Okay. So let's say that before splitting the entropy is 0.94. After splitting also entropy is 0.94. Is it reducing any impurity?
No.
No, sir.
No, it's not reducing, right? Let's say before splitting entropy is 0.94. After splitting entropy is 0.3. It's reducing, right? Reducing
Yes,
with
sir.
what? 0.94 minus 0.3, which is 0.64. So this is the gain, expected reduction in the entropy. So whichever the attribute reducing the impurity more, you select that attribute. To understand this, you subtracting it. Got it?
Yes, sir.
Yeah. Okay, so let us continue with this example. I got the overall idea, right?
Yes, sir.
Yeah. So this is the entropy of outlook sunny. Outlook sunny, 2 positive, 3 negative, as we have already seen. This is the entropy value here, which is 0.97. And compute the entropy of overcast. Outlook equal to overcast, as we have already seen. How many overcast examples? 1, 2, 3, 4. And all of them are positive. So 4 positive, 0 negative. So this is the entropy value, which is 0. You can directly say this. If all the instances belong to one class only, then entropy is 0, right? You need not compute.
sir.
You can directly say that. All right. Two things you can directly say when you have equal number of instances from both the classes. What is the entropy value?
0.
0.
No, equal number of instances from both the
Sir,
classes.
1.
1, right? So when you have instances belong to, all the instances belong to only one class, then
0.
0, right? Like this case. Now next one, what is the entropy of outlook equivalent to rain? Outlook equal to rain, we have 5 instances, this 3, 1 and 1. Out of them, 3 of them are positive, 2 of them are negative. So for this also, entropy value is 0.971. So now can you compute the gain now? What is the gain? 0.94, it means the entropy before splitting minus entropy after splitting. 0.971 multiplied with the corresponding fraction of the examples here. So how many fraction of examples are here? Outlook equal to sunny? 5 by 14, right?
14.
Right? Total 14, out of them 5 of them are sunny. Am I right?
Yes,
5
sir.
of them are sunny. Plus, how many of them are overcast?
4.
4, right? So 0 multiplied by 4 by 14 plus 0.971 multiplied by
5.
how many of them are
5.
rainy? 5 by 14. This is the weighted fraction of the entropy we are computing after splitting. So this is what we compute. All right. So this is directly computing for every attribute value. So this is the temperature hot. Temperature hot, how many are there? Hot. This 3. One more.
4.
And 2 of them are negative. 2 of them are positive. So equal number of positive and negative. What is the entropy? 1. Right. So temperature, what are the other possible values for the temperature?
So
Mild and
mild,
cold.
cold.
Temperature mild or moderate is 4 positive, 2 negative. There are 6. You can check that. 1, 2, 3, 4, 5, 6. So 4 of them are positive, 2 of them are negative. Entropy value is 0.918. Similarly, entropy, temperature equal to cold. There are 4 instances. 3 of them are positive, 1 of them is negative. Entropy value is 0.811. So can you tell me the next one? Humidity. How many possible values?
Sir,
2,
2.
right? High and normal.
Yes,
How
sir.
many high? 4, 5, 6, 7.
7.
7.
7. How many positive? How many
7.
negative? High.
Sir,
How many positive?
2. Sir, 4 negative.
4 negative, 3 positive.
Yes, sir.
Okay, so the entropy value is 0.985. How many humidity normal? 7 again.
Yes, sir. Total 7.
How many positive? How many negative?
Sir, 6 positive and 1
One
negative.
That is 0.592 is the entropy value. The next one is the wind. Compute the wind. How many possible values? Wind strong, wind weak.
2.
Right. 6 positive, 2 negative, 0.811. Wind strong, 3 positive, 3 negative, it is 1. So we have computed entropy with respect to each and every split, with each and every attribute split. Now we have to compute the gain. So to compute the gain, take the entropy before splitting and after splitting. So this is the entropy 0.94 before splitting. This is the entropy of the outlook multiplied with the corresponding fraction of the instances. Entropy of outlook equal to overcast multiplied with the corresponding fraction of instances. Entropy of outlook equal to rainy multiplied with the corresponding fraction of instances. 0.94 minus 5 by 14. Why 5 here? 5 instances are outlook equal to sunny multiplied with the corresponding entropy. Why 4 here? 4 instances are outlook equal to overcast. And why 5 here? 5 instances are outlook equal to rain. Right? So you got 0.24, which is the gain with respect to outlook. Okay. Similarly, compute the gain with respect to temperature, which is 0.0291. Compute the gain with respect to humidity, which is 0.151. And compute the gain with respect to wind, which is 0.048. So now we select the attribute that maximizes the gain. So according to that, which attribute should we select? Outlook, or temperature, or humidity, or wind? We select outlook, right? For which the gain is 0.24, which is greater than these 3 values, right? So we select the outlook in the root node. Is the process clear to everybody?
Yes, sir.
Yes, sir.
Adams?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. So now we select this outlook in the root node. If you select the outlook in the root node, what is the split? Split of the possible attribute values are sunny, overcast, and rainy. At sunny, you will get 5 instances: D1, day 1, day 2, day 8, day 9, and day 11. And 2 of them are positive, 3 of them are negative. Is it pure? Is it pure?
No.
Not at a pure, right?
No.
Not pure. You have, it requires further splitting. What about this? Overcast, you got 4 positive and 0 negative. Is it pure?
Pure, pure. It is pure, sir.
It is pure. So therefore, you assign a label S to it. You can make it as the leaf node and define a label S. What about this? This is also not pure. It requires further splitting. Okay. So now the question is, what attribute should we select at these nodes?
You have to recalculate the same similar.
We have to repeat the process, right? So now in this path, outlook attribute is already checked. So you need not check for the outlook attribute again, but you can check it with respect to the other attributes. It means entropy before splitting, entropy after splitting. So what is the entropy before splitting? You now take this as a data set and repeat the process. So what is the entropy before splitting? 2 positive, 3 negative. It means 2 by 5 log 2 by 5 minus 2 by 5 log 2 by 5 minus 3 by 5 log 3 by 5. This is the entropy before splitting, right? You just take the sunny instances. So please listen carefully. So what is the entropy before splitting? Minus 2 by 5 log 2 by 5 minus 3 by 5 log 3 by 5. I think it, if I remember correctly, it was minus 0.971. This is the entropy before splitting. Suppose now if I split it based on the temperature, split it based on the temperature, split it based on the temperature. Okay, what are the possible values? Temperature equal to hot. Okay, so how many of these 5 instances temperature equal to hot?
So 2.
2. Only 2.
Yes,
Right?
sir.
Only 2. And how many of them are positive and how many of them are negative?
So both negative.
Both negative, right? So it means if I split it based on the outlook, right, entropy after splitting is, for the value temperature equal to hot, after splitting entropy is 0,
Yes, sir.
right? So what is the next? Mild. How many sunny are, I mean, how many temperatures are mild out of this 5?
So
Out of
2.
this 5? 2. How many of them are S? How many of them are no?
1
One S,
positive, 1 negative.
1 negative. So the entropy
Yes, sir.
is
1.
1. The next one,
Cool.
cool. Only 1 and that is S. Entropy is 0. So entropy before splitting is 0.971. What is the entropy after splitting?
1 into
0 into 2 by 5 plus 1 into 2 by 5 plus 0 into 1 by 5. Am I right?
yes, sir.
Right. So 0 entropy here, 2 instances are there, 2 by 5. 1 entropy here, 2 instances are there, that is why 2 by 5. 0 entropy here, only 1 instance is there, right? So this is total 2 by 5, which is 0.4. 0.4 only, right? Yes, 0.4. So what is the expected reduction in the entropy, which means what is the gain with respect to the temperature? 0.971 minus 0.4. 0.57. Similarly, compute the gain for humidity for the wind. Whichever attribute maximizes the gain, you select that attribute. Clear, right? Procedure clear, right?
Yes,
We'll
sir.
be repeating the same process at that in recursively defining repeating the same process. All right. So yeah, so compute the entropy of outlook sunny 0.971, which is the entropy before splitting. Then compute the temperature hot, entropy is 0, temperature mild, entropy is 1, temperature cool, entropy is 0. Now gain you compute, which means the entropy before splitting 0.971 minus the entropy after splitting, which is equivalent to 0.571, that whatever that we have computed just now, right? Similarly, compute the gain for humidity right? Humidity gain, which is equivalent to 0.971, and compute the gain for the wind, okay, so which is equivalent to 0.020. So which is the best, temperature or humidity or wind? If you don't remember, for temperature we got 0.571 as the gain. For the humidity we got 0.971 as the gain. For the wind we got 0.020 as the gain.
I think will be there.
What is the best attribute?
Humidity.
Humidity is the best attribute. So select the humidity. If you select the humidity high, humidity normal, 3 instances are coming here, all of them are negative. So assign a no here. Humidity normal, 2 positive instances are coming, right? Assign S here. Okay, similarly repeat the process here also. Okay. Okay, this already discussed, splitting based on the continuous attributes. This what is that? I did this slides. I don't know. Okay. These are the slides that are not planned in your syllabus, right? So I'm avoiding that. So I think that's all. Okay, one more slide I have to wait. Okay, so now you are trying to have you understood how to build the tree construction based on the gain or the entropy values,
Yes, sir.
right? So now what happens is that if you allow it to do, like if you split further and so on, there is sometimes a possibility of overfitting. What is overfitting? Overfitting results in the decision tree that are more complex than necessary. It means if you are making the decision tree more bushy, like so many branches and so many depth, I mean, you are extending it to so much depth, then there is a possibility of the overfitting, right? So training error no longer provides a good estimate of how well the tree will perform on the previously unseen records. Or in simple words, the training error may be good, but it performs very poorly on the test instances. That is what is the overfitting problem, right? Overfitting is a situation where the model performs very well on the training data, but very poorly on the test data, right? So it means if you go very specifically point to point, right, then you may create a more and more conditions. It means you are making this depth of the tree more and more. Then as a result, what will happen is that it will work specific to that training data only. It means given any new data, it may fail. It means it will perform worse on the test instances or the new instances that the model has not seen, right? So this situation, we call it as a overfitting problem. So there are two ways of avoiding overfitting problem in the decision trees. One is pre-pruning. The other one is the post-pruning. Pre-pruning, post-pruning. Pre-pruning is we are not allowing the tree to grow too complex. It means we are setting some limits by some means. Like for example, I can set a condition that depth of the tree shouldn't be more than 5. Okay, it will not allow it further. Okay, so suppose if the depth is like 5, like depth is 5, somewhere here 5, and here further there is no purity. I mean, though the depth is reaching to 5, there is no purity. Let's say that 8 of them are positive, 2 of them are negative. It's still not pure, but you are setting the limit here. Okay, it means you shouldn't extend it beyond this. So what label should I, it means you have to make this as a leaf node. Which label should I assign? Yes or no? We assign yes because majority of them are from positive class, isn't it? So we assign a label positive here. Similarly, let's say that here somewhere here, all right. So there are 15 instances. Let's say 12 of them are negative and 3 of them are positive. It's still not pure, but you have to stop here. Which label would you assign? Which label would you assign? Nobody is following.
No.
Anybody? Understood or not? First of all, have you understood what is the overfitting problem?
Yes, yes, yes.
Yes. So now I am discussing the pre-pruning technique. In pre-pruning technique, I am discussing one possibility, which is setting the limit on the depth of the tree. So now you may ask a question that if you set the limit on the depth, if at that depth, if the node is still not pure, what will you do? So like that, I'm giving an example. Let's say at level 5, let's say that depth limit is 5. You set the depth limit as 5, and this node is still not pure. 8 positive and 2 negative are there. But you have to take a hard decision of making it as a leaf node. If you have to make it as a leaf node, you have to assign a label. Which label would you assign? Positive label or negative label?
Positive.
Positive, because majority of them are from positive. Similarly, let's say that here 12 of them are negative, 3 of them are positive. Which label would you assign?
Negative.
Negative label. Like that we can decide. This is one possibility, setting the depth on the limit. The other possibility is, let's say that if you have let's say you set threshold on the number of instances. Let's say that if the number of instances less than 20, less than or equal to 20, you will not proceed further. You will stop that at that node, right? You will not split it further. This is one possibility. Or you can set a condition like um, if fraction of I mean um, if more than 90% of the instances are belong to only one class, then I will not proceed further. I will stop there. So these are the various conditions that you can adopt for the pre-pruning, right? All of them are not allowing the tree to grow too big, right? So these are all the pre-processing, pre-pruning techniques. Have you understood the concept of pre-pruning? Pre-pruning. Have you understood the concept
Sir.
of pre-pruning?
Yes, sir.
Now post-pruning. Post-pruning allows the tree to grow as big as it grows. Okay, it will not set any limit. It will allow to grow. It will allow the tree to grow till to the maximum extent possible, right? So after that, what it will do is that
So,
it will work.
sir, if we are going with the pre-pruning, I think we are not properly utilizing the resources. First tree
No,
is
not like
generated,
that.
then the tree is pruned.
That depends, madam. Like for example, if it is too much restrictive, let's say the depth equal to 1 you said. Okay, what you said is right. Fine. So it depends on the problem at hand and how much, I mean, what is the limits that you are setting. You are true to some extent, you are right to some extent, in a sense that if you make the model too restrictive, it means you are not providing the model the flexibility to learn the complex patterns in the data. Okay, but if you give the flexibility, but at the same time you are controlling the overfit, that chance also there in pre-pruning. It's all depends on what parameters that you take for pre-pruning. And this is a kind of something like you have to try multiple things and see which is working good. It's not that you fix some depth and that is you finalize that. Suppose you said pre-pruning is the depth of 3. It's not that, I mean, you're selecting pre-pruning technique via depth of the tree, by limiting the depth of the tree. It's not that you will be checking, you're setting one depth limit and finalizing it. you'll be checking multiple depth values. What is the error at depth 1, error at depth 2, error at depth 3, depth 4. Like that, multiple values you try, whichever the depth is minimizing the error, you select that depth. It's a kind of hyperparameter to tune.
Yeah,
Got it,
yes.
madam?
Yeah, sir.
Yeah. So post pruning, you allow the tree to grow as big as it grows. Okay. After that, try to prune it. Like for example, I prune this branch. So before pruning this branch, measure the error, validation error with respect to the validation data set. Right. After pruning, also find out the error. So let's say before pruning, error is 0.6. After pruning, error is 0.5. So what should I decide? Should I prune the tree or shouldn't prune the tree? Error is decreasing, right? After pruning, it means don't revert back the changes. Suppose after pruning, the error is increased to 0.7, then revert back the change. Like that, repeat this process for all the branches at each and every level. Got the point? Okay. So
Checking the parent node value.
with the tree as it is, compute the error with respect to the validation data set. Okay, let the error is 0.6. Compute prune off one branch. Let's say this branch you are pruning off. After pruning off, compute this error. Let's say it is 0.5. Error before pruning is 0.6. Error after pruning is 0.5. Is it improving or not? Error is reduced or not? Improved, right? Improving means error is reduced. Hello, everybody.
Yes, sir.
Overload, right? So it means by cutting off this branch, the performance of the model is increasing. Therefore, cut off this. You need not revert back the changes. Now prune off this branch. Let's say before this splitting, before pruning of 0.5, after splitting it is 0.4. Is it improving or not? Performance is improving, right? Right? So if it is improving, just make this change permanent. Okay. So let's say before pruning of this branch, error is 0.5. After pruning of this branch, error is 0.45. Is the performance increasing or decreasing? From here to here?
Decreasing.
Decreasing, right? Because the error is increasing. So therefore revert back the change. Don't make the change permanent. Like this, we'll be doing. It can be top down also, it can be bottom up also, right? This is the post pruning idea behind the post pruning. You allow the tree to grow as big as it grows. After that, try to cut off the branches one by one and see that which one of the branch, if by cutting off that branch, is the performance is increasing or decreasing. If the performance is increasing, make the change permanent. Otherwise, revert back the change. Got the idea? Post pruning.
Sir, if you are pruning like this, then some of the classes will not be coming under the decision also.
It will come, madam. Like for example, if you are pruning this, now it means you have to make the decision based on the instances at this node, right? After pruning of this. So let's say there are 10 instances here. Out of this 10, let's say that 7 of them are positive, 3 of them are negative. So we make this as a leaf node and assign a positive label to this because majority of them are positive.
Even the negative one will take it in the positive sense. Even the 3 things will be taken in the positive.
Yes. 3 things will not be there. No? That is a model that you are building based on the training data. So you will be assigning majority label. Once this model is built, you have nothing to do with this training data. Training data is not required. You'll be only testing with respect to the new instance.
Okay.
Yeah. Got the idea? Just the idea I'm asking. Pre-pruning and post-pruning. Have you understood the ideas behind that? Intuition behind that? Okay. All right. So that's all because I think you're also overloaded. So I'm winding up here. Before that, let me also quickly demonstrate this hands-on. It is easy. So let us complete. It takes another 2-3 minutes. Let us complete. I hope at least you followed till the tree construction part.
Yes, sir.
Decision tree classifier. So import all the required libraries. So everything else you know. Only thing that are new here is that decision tree classifier, which is we are importing from sklearn.tree. Another thing that we are importing here is plot tree, which is to visualize the tree. Okay. So now I'm importing the required libraries. Second step is reading the dataset. Here I am reading the diabetes dataset, diabetes.csv. Okay, so this is how the data looks like. You have already seen this in case of SVM, so I'm not focusing on that again. The next one is prepare the dataset. Just drop out the last column. Remaining columns you are taking as X. Just the last column you are accessing, that is Y. This is preparing the dataset. Okay, so what next? After preparation of the dataset, what next? Splitting the dataset into training and testing. We call the train test split. Okay, so test size is 0.3 here. We split the dataset. Then build the model. I call the decision tree classifier. By default, this criterion is Gini indexing. If you want to change it to entropy or any other method, any other criterion, you have to explicitly set that. So your classifier, you are fitting it for the training data and predicting for the test data, and then evaluate this measure. Okay, evaluate the accuracy score. So if you want to split it based on the other evaluation criterion, then you have to explicitly set the criterion function, entropy. And this is the max depth, which is the kind of pre-pruning technique, right? Limiting the depth. Okay, so classifier.predict, classifier.predict, measure the accuracy. So here it is an accuracy of some 0.77. Now plot the classifier. It means if you want to plot the tree, call this plot tree and pass the model as the input for this. So you see that. So this is how it looks like. Where is this? You see that. This is how the tree looks like. The tree looks little clumsy. So let me just set the depth to only 2 to show you the tree. Okay. Or 1, depth equal to 1, or 1 I am setting to make it clear. You see that. This is the decision tree. This is how it looks like. This is the decision at the root node, and this is the decision at the next internal node. Okay. Okay. So you see that. Okay. So this is the indication of how many of them are positive, how many of them are negative. 354 positive, 183 negative here. Right. Total number of samples is 537 and entropy is 0.926. So like this, you can visualize the tree by calling this plot tree option. Got it? Any query?
So where is the
Anybody?
parameter in that tree, sir?
Madam?
Parameter in that tree, sir? Which classification we are doing?
I couldn't get your question. Can you please repeat if you don't mind?
Sir, we are getting the constraint by the parameters. No, sir. Where is the parameter we are getting it, sir? In the tree. I want to see the tree.
Max depth, you are taking max depth. You're asking about max depth.
Oh, sir, the final decision tree.
Decision tree, okay. Yeah, this one. The first one is the condition, madam. The second one is the entropy value. Number of samples at that node. How many of them are positive and how many of them are negative?
Okay.
Similarly, here, okay, 0.72 is the entropy value. Number of samples is 342. Value is 27. I can give the depth too so that you will understand it better. Okay. Yeah, now you see this. This is the condition at the root node. and this is the condition at the left node. This is the condition at the right node. Okay. And this is the entropy values, number of samples at that node, and how many of them are positive and how many of them are negative. Got it, madam?
Yes, sir.
Yeah. So any other query?
No, sir.
All right. All right then. Thank you very much and happy learning. Good night.
Thank you, sir. Good night, sir.
Thank you, sir.
Thank you, sir.